Okay, so now we have a handle on some representations, right? Last time we talked about the fact that I'm going to share my screen. Uh, so last time we talked about representations, we were talking about representations and, GLN of QP. And I mentioned that I should say, smooth irreducible representations, which, by the way, smooth plus irreducible, famous result, implies admissible. But in general, we're just going to focus on, those representations. Even if they're not irreducible, we want them to be both smooth and admissible. All the smooth irreducible representations of GLN were one-dimensional, which is to say they're simply given by characters. And then, or sorry, all the finite dimensional ones, right? So we have this like complete characterization, basically the one-dimensional representations, and now we've got to jump up to infinite dimensional vector spaces to try and get a hold on this. So, gosh, how do we how do we do that? How do we even begin to access the infinite dimensional? Um, and well, I'll also just mention, we have a complete classification of these characters, right? So there was the ones that were trivial on the maximal compact. So sometimes it's um, written with a K. So this was just GLN of the p-adic integers. And so the ones that satisfied that had the property, remember that they were just, the determinant, and then you take your p-adic absolute value, put it to the power of some complex number. And then we also had, so these were the unramified ones, which is mostly what we're going to care about, at least for now. And then the ramified ones, those are all a matter of, well, basically, we want to understand, the so-called ramified characters of ZP cross. But there's, I was just talking with my good friend and colleague on a hike the other day yesterday about the decomposition and how to classify the I can't remember how this splits up, but it somehow just comes down to I should have prepared this, but I want to focus on unramified anyways, but um it basically just comes down to understanding like characters of finite abelian groups. Um, so that takes care of the ramified ones. But I'm gonna brush that under the rug, but in general, there's sort of the representation theory, and we'll see this in a different way later on, can sort of be split into sort of two sections, right? The ramified and the unramified. There's this word. Okay, I'm not going to explain what it means now, but we will get to it. There's unramified representations and supracuspidal representations, more generally for the case of GLN, and in the much more general case as well. So the unramified representations are, I would say, pretty well understood. There's a very nice theory. That's pretty much what we're going to dive into right away. And then there's this sort of there's hospital representations or supracuspidal representations, and there's a whole industry of constructing supracuspidal representation. So that's almost like a branch of representation theory unto itself. And then there's a bunch of results that we'll see down the road that sort of, the way I first learned it is I just black box this part of the theory. And then there's another part of this theory that says, okay, suppose you have whatever these mysterious supracuspidals are. Now here's a recipe to build more general representations. So we're going to start off black boxing that, and then, hopefully we'll dive into it at some point. Okay. But let's get I'm getting off tangent. I'm talking about abstract things. Let's come back down to earth. Let's talk about how do we access more of these representations, and we know that they have to be infinite dimensional. Well, if you studied representation theory in any capacity before, you know that we have two very important operations. Okay, if you happen to speak category theory, these are a pair of adjoint functors. But even if you don't speak that, hopefully you're familiar with the idea of first off, restriction. So that just takes a representation of a group G, right? So pi V, pi is a homomorphism from G to GLV. And then you get a representation of, if H is a subgroup of G, you get a representation by simply just restricting the domain. Yeah. And there's a sort of nice operation that has a special relationship with restriction going in the other way. Again, if you happen to know the fancy terms, it's a pair of adjoint functors. And induction, remember, so that says if I had, W sigma of a representation, then the being a representation of H, then the induced representation, well, the underlying vector space is going to be given by, and right now, yeah, is going to be given by functions, all functions from G to V, such that f h x is sigma h f of x, right? So this is the underlying vector space. It's all functions satisfying this property, where of course this has to hold for all h and h and all x and g, and where the action of the group G on this vector space is given by right translation. So right, in order to tell you where G dot F, where that function is, I just have to tell you what it does to each element X, and it's simply going to be translated on the right? So that's just like normal, when you first look at the representation theory of finite groups. This is the induced representation that you see. And it's really important, right? We use the induced representation. Am I blowing my microphone? Am I way too loud right now? We're using the induced representation in so many different it's very, very useful, right? So like we can use it to construct a lot of representations for us, right? And we have things, there's also like the so-called the standard representation of a finite group, where we have G acting on CG, right, which is the space of all functions, complex valued functions on G, and all of our irreducibles, show up in here, right? So, maybe by using induction here in this world, we can sort of get at more irreducible representations, including possibly our infinite dimensional ones. Because, so of course, in the finite group world, right, where of course we only have our vector space is going to be finite, our vector space of functions will be finite dimensional. But if I have now our group is GLNQP, so this is some big infinite group, right? So yeah, our space of functions is going to be infinite dimensional. Of course, we have topological considerations to worry about, though, right? Because we want our representations, again, I want a representation to be smooth and admissible, right? So if I have some representation W sigma of a subgroup H of GLN, well, then I want to make sure that if I induce this, right, GH, if I take my induced representation, this should be a smooth irreducible representation of G, right? So I should say, remind you, or maybe tell you, if I didn't say in the last video, when I'm talking about rep G and rep H, I'm talking about the categories, or just think collection, of all representations that are smooth and admissible, right? So I want to make sure that if I induce a smooth admissible representation, I get one. If we look up, right, we say, okay, I'm just going to copy my classic definition of induction. Well, it's not so clear that that's going to happen, right? Because there's nothing in my definition of induction that really talks about the topology, right? This just says all functions from G to V, right? So probably what I'm going to want to do is replace this with all smooth functions, right? And in particular, well, there's another way to argue this actually. Let me say this. I'm gonna talk a little freely in this next part, so I might say something wrong. It might be a tiny bit sketchy. But let me mention one other thing. Because there might be there's this question of like, well, what if I had a representation V and pi, which was a representation of G that was maybe not smooth, right? Could I get a smooth representation? Well, we can define a subspace, so VSM for V smooth. So this is going to be all of the vectors in my vector space, such that the stabilizer is open. And I claim that this is a subrepresentation, right? So, well, let's think about it. I mean, if I had a V whose stabilizer was open and I act on it by G, now I ask, what's the stabilizer of this thing? Well, of course, it's just going to be the stabilizer. I'll write stab. The stabilizer of V and just conjugated by G, right? So everything in here will stabilize this and vice versa. And then I suppose I have to convince you, or maybe for now I'll just hope you believe, because right now, we're doing things more of a general overview. Eventually, I'll get to more technical proofs, but I'm just in an explaining kind of mood right now. The other thing I want to convince you of, well, it follows pretty quickly from the axioms of a topological group, right? That conjugation will preserve this open set, right? More or less, it just comes from the fact that I mean, in our axioms of a topological group, we demand that our multiplication is a continuous map, as well as the map that sends an element to its inverse. We demand that both of these things are continuous. And so, indeed, this will preserve open sets. So the smooth vectors then will give you a representation. And in fact, you'll get a smooth representation, right? Because by definition, everything in here has open stabilizers. So what we want to do then is, my proposal is essentially you take what would normally be the induced representation, and then you simply take the smooth vectors. Now, it's not really presented in this way, and it's not clear from this that if we start with an admissible representation, we get an admissible representation. Like, those things all need to be proved. So let me just give you the definition that we normally see. So, well, different authors use different notations, and I might be going against the grain here if I read it this way, but for us, so we're going to drop the smooth part because implicitly we want everything to be smooth anyway. So for us, if we induce, and we're going to want to also add the condition that not only is H a subgroup, but it's closed. Then for us, the induced representation of with respect to some subgroup is going to be the functions from G to V, again, satisfying this same property, except now, once we take this sort of smoothness condition, a more common way that it's written, at least, I've got Bump's book on automorphic representations open at the moment. There should be one extra condition on the functions in the set, and that's for each of these f, there exists an open subgroup u sub f of g such that f x u is fx for all u in u, right? So that's our smoothness condition. And it is a theorem that this definition of induction preserves admissibility. So fantastic. Something else that you might be wondering about is, actually, do I want to talk about that? Yes, you know it's important. Yeah, okay. I'll mention it now. So, if you again have studied representation theory in any sort of capacity, you know that, and I could be messing it up which side the adjunction goes on. Restriction is adjoint to induction. If you happen to really know your abstract nonsense, generally, and again, forgive me if I have my adjunctions on the wrong side here. Forgetful functors generally come in pairs with free functors, and one's on the left and one's on the right. What does this mean? Okay, there's a less abstract way to explain this. I don't want to scare people off who are coming without an abstract background. This boils down to a result called Frobenius reciprocity. So I probably should have just opened with that, right? That the Frobenius reciprocity is this relationship between induction and restriction. Again, very useful tool if you've done representation theory before. And we might wonder if there's a corresponding statement with respect to our induction here. In fact, there is, but yeah. Yeah, so there's just so we still have an induction and restriction adjointness. But now let's start thinking about oh, something weird's happening on my computer. Let's start thinking about how are we actually going to do this, right? How are we going to make use of this? Because in order to make any use of induction, right, I need to know things. I need to know like nice subgroups, and I need to know representations of those subgroups, right? So the only representations we know about right now are the characters, right? In particular, well, I suppose we have all sorts of characters, but we know about characters for GLN, right? We're not talking about any other kinds of p-adic groups yet. And so you might be like, well, what kind of weirdo, crazy, oddball subgroups of GLN could possibly exist, right? Well, one thing that maybe, if you sit down and you think about it for a little bit, you've got some, you know, experience with working with matrices before is, we can break up matrices in block diagonal form, right? This is something that happens a lot, right? We break up matrices in block diagonal form. And so we have these subgroups of GLN, which are themselves just products of GLN, right? So if I have any partition n1 up to nr of n, then this partition determines a subgroup. So sometimes it's used with an M, sometimes with an L, but it determines a subgroup of GLN, which is just isomorphic to GL. I'm going to suppress the QP notation, but it's just isomorphic to this product of GLNs, where exactly, right, an element X of MN1 up to NR is of the form X1 down to XR, zeros on the off diagonal, where of course XI is in GLNI. Great. So, this is fantastic for us who were only thinking about GLN at this point. And we realize, okay, maybe we can use induction of characters to take these finite dimensional, to sort of access these larger infinite dimensional representations. And we have a bunch of subgroups that are just a bunch of copies of smaller GLNs, right? So what we're going to try to do then is access these representations by inducing from Levy subgroups. Oh yeah, so by the way, for GLN, these are all examples of Levy subgroups. And in fact, this exhausts, well, up to conjugation, the Levy subgroups. So if you don't know what those are yet, I'll probably be making some videos on algebraic groups soon enough. So that comes up in there. Don't worry about it. This is just a name for now, but they're special subgroups. And there's a lot of reasons why these are important and worth focusing on. Besides our own justification of like, wow, GLN's all we're thinking about. So that's all we're going to focus on. So what we're going to do then is M1 up to NR. Basically, we're going to look at induced representations where I'll just take some characters, and by writing this box, I mean what's called the external tensor product of representations. So if you haven't seen this before, or even if you have, let me just remind you, if I have two groups, G and H, and I have representations, V rho and W pi of these groups, then the external tensor product of these representations I will define to be, well, of course, on the underlying vector spaces, we have the usual tensor product, but now the box product is going to be given by, well, it's the pretty obvious thing, right? So if I have rho pi on a pair GH, how is that going to act on a simple tensor VW? Well, you can probably guess. Rho G is going to act on the V. Pi H will act on the W. That defines it on simple tensors, and then we extend bilinearity to get it on all tensors. Well, we're dealing with vector spaces, so our tensor products are very nice. Yeah, so that's tensor products. And so now here is a way for us. So let me, I guess we'll just back up, right? We have a complete understanding of one-dimensional representations for GLN. We're going to take whatever GLN we're working with, look at these subgroups that break up into copies of smaller GLNs, and then induce the plunk a character down in each factor, because again, that's basically all we know about at this point, and we're going to induce this thing. And this is now our hope for generating infinite dimensional, and then hopefully looking inside of these induced representations to find new irreducible representations. So I think that's where I'm going to leave it off now. That's just sort of the explanation, and then we're going to maybe get into some more slightly more technical weeds in the next video. So I'll see you then, and yeah.